Okay, let's talk about this big picture, this autoregulation big picture. Um, and let's just work through this. I know it's intimidating when you first look at it. You've got multiple receptors, you've got three separate control centers, you've got effectors all over the place, but really what we're looking at here is we're just looking at autoregulation. So in here we've got hypovolemic shock. So we've got decreased blood volume. Remember, hypovolemic. So we have a shock situation, the result of decreased blood volume. So what's going to happen is I've got a decreased blood volume, and consequently I've got a decreased blood pressure. So we're going to come back and we're going to say, okay, how does the body know that that's going on? Well, the receptors, those same receptors that we've talked about time and again, we're going to add another set of receptors to that conversation, but the baroreceptors on the right in the aortic arch and the carotid sinus, and then the baroreceptors in the kidneys. So there are pressure receptor sensors in the juxtaglomerular cells. I know that doesn't mean a lot right at the moment. Juxtaglomerular will mean more later when we get to the renal chapter. But we do have these baroreceptors in the kidneys. So let's start down the left side of this chart. When those baroreceptors in the kidneys don't stretch as far as they normally would, what's going to happen is the cells there are going to release a hormone. That biochemical response is renin. So we're going to see an increased secretion of renin. Renin is actually going to function to work with something called angiotensinogen in the blood. So we're going to have increased renin, which means we're going to have the release of angiotensinogen in the blood. We're going to have an output, and that output is the conversion of angiotensinogen to angiotensin 1 and then subsequently to angiotensin 2. Angiotensin 2 does two things. What it does in the adrenal cortex is it stimulates the cells in the zona glomerulosa to liberate aldosterone. The job of aldosterone is to act on the kidneys. Aldosterone acting on the kidneys are going to have them conserve salt and conserve water, to not lose that salt and that water out through the urine. And what we're going to do by retaining that salt and water is we're going to increase the blood volume. The other thing that angiotensin 2 does is it causes a localized or even a systemic vasoconstriction. By decreasing the lumen size in those vessels, we're going to increase vascular resistance, and as we've said time and again, increased vascular resistance means an increase in blood pressure. So now I want you to loop all the way back up to those baroreceptors again in the blue box, and let's talk about the baroreceptors in the aortic arch and the carotid sinus. Remember, they're not stretching as much, and when they don't stretch as much, they're going to send an increased rate of impulses to the control centers. In this case, we're talking about two control centers. One we've talked about before. That's the one on the right. That's the cardiovascular center in the medulla oblongata. And when the medulla oblongata receives fewer impulses from the baroreceptors than it's supposed to, its response is to go, oh, crud, and send out increased sympathetic stimulation. So we're going to see an increased sympathetic stimulation, and we're also going to see hormones coming from the adrenal medulla. Okay, so remember the hormones from the adrenal medulla were who? Yes, exactly. Epinephrine and norepinephrine, those catecholamines. What are they going to do? Two things. They're going to cause vasoconstriction, constriction of those blood vessels, which is going to result in increased peripheral resistance. Increased resistance means increased blood pressure. The other thing we're going to see those catecholamines do, that epi and norepi, is we're going to see an increased heart rate, so that heart's going to beat faster. We're also going to see an increase in force of contractility. Those muscle fibers are going to contract more forcefully. If we increase the heart rate and we increase the force of contractility, we're going to increase the cardiac output and the stroke volume, and if we do that, we're going to see an increased blood pressure. We're going to go back to that middle control center. So remember, we're at the baroreceptors from the aortic arch and the carotid sinus. They're sending decreased nerve pulses, and one of the places that's going to respond to that is the hypothalamus and the posterior pituitary. Remember that the hypothalamus stores two specific hormones in the posterior pituitary, that being the antidiuretic hormone and the oxytocin. In this case, we want to talk about ADH, or antidiuretic hormone. Antidiuretic hormone is going to leave the posterior pituitary, or the neurohypophysis, and is going to enter into the bloodstream. That's going to have two effector responses. The first one is ADH is going to act directly on the kidneys, resulting in a conservation of salt and water. That conservation of salt and water is going to increase blood volume. The second function of ADH is to constrict blood vessels. So that vasoconstriction, as we've said a couple of times now, is going to increase peripheral resistance. Increasing that resistance is going to cause an increased blood pressure. All of these big picture things are going to continue. We're going to see the angiotensinogen, we're going to see the hypothalamic and posterior pituitary response, we're going to see the medulla oblongata response, all of that, and ultimately the effectors, all that will continue until we offset the original problem. And the original problem was that we had decreased blood volume and blood pressure due to hypovolemic shock. So once we get that blood pressure and that blood volume back up to normal, the baroreceptors in the kidneys and the baroreceptors in the aortic arch and carotid sinus are all going to return to normal, and we're going to not need to have those actions of the control center and the effectors go on. Remember that autoregulation of blood pressure and blood flow is really just, it's a complex interplay. I've got multiple systems. I've got vascular, I've got nervous system, I've got endocrine system, I've got these hormones and everything floating around. I've got involvement of the adrenal gland, the kidney, the heart, the peripheral vasculature. All of these guys are just really truly about getting this autoregulation back and maintaining homeostasis, offsetting that original problem, which in this case was hypovolemic shock. I hope that helps. Listen to it again, shoot me some questions. Office hours are always a good time to go over it if you want. Just let me know if it's not working for you, because we are going to see this, maybe not this directly, the diagram, but questions about this concept on our exam.